Hey guys, it's Dr. Thomas. We're starting chapter 12. Again, this is 1212 lecture, following the PowerPoint that can be found in D2L. This video is going to be one of the shorter ones that we do. It's going to be kind of just an overview of chapter 12. A lot of the information you're going to have to learn by reading the chapter, but I'm going to kind of give you some guidelines on what I expect you to know. And at the very end, there's a problem that we're going to work just to show an example of the type of problems that you might have to do on the test. So, first of all, this chapter, again, it focuses on solids. There's a different section for a lot of the different types of solids that we can encounter. You can have ionic solids, metallic solids, molecular solids, covalent network solids, all those different versions and more. But what I want you to know for each one, as you read through each section, don't get too bogged down in the details and when it gets into some kind of strange topics, but you do want to know for each type of solid, you need to be able to give a pretty general description of the properties of that solid in terms of like how the atoms are arranged, what kind of forces hold the molecules together, or the atoms or species or whatever they are. So have a general description. For each one, there may be certain terms that are important, like when you study ionic compounds, they exist in a crystal lattice. If you look closely at the structure, you can define the unit cell of the crystal lattice. So those would be important terms that would relate to ionic compounds and ionic solids. So make sure you know those. And then when you learn about each solid, you want to know what are the general properties that that solid would exhibit. This can be things like metals tend to be shiny. They tend to, if you hammer on a metal, most metals are fairly ductile. On the other hand, if you use a hammer on a crystal structure, they tend to be more brittle and they shatter. If you talk about conductivity, some solids are good conductors of electricity. Other solids are good conductors of heat. So those are just some of the things you might look at for the properties that you're looking at for each solid. And then finally, for each one, it'd be nice if you knew a few common examples. For instance, a covalent network solid, the two examples that are used most often, diamond is a covalent network solid, and another one is quartz, which is a silicon dioxide. It's one of the forms that silicon dioxide can take. So just be aware of those. And then the rest of the PowerPoint, for the most part, kind of just goes through the types of solids. Again, there's a little bit of information here. Supplement it from your reading, but stick to the items I listed on the previous slide, and that'll be a good guideline for what you need to know. So specifically, a couple of things as we go through. When you look at crystal lattices, there are a lot of different forms that you can arrange the atoms in. Specifically, the three that you need to be familiar with are the primitive cubic lattice, which is sometimes called simple cubic, the body-centered cubic lattice, and the face-centered cubic lattice. For those three in particular, those are the ones that I might expect you to know how the atoms are arranged, and then the math problems that we're going to do could be based off of any of those three. Okay? Now, when we look at these crystal structures, we sometimes need to figure out, okay, from each unit cell that we're looking at, how much of an atom is actually inside the unit cell when it's at the different positions that are possible. Okay? Now, to simplify that, if we start with the simple cubic cell, essentially what that is in the cube, there's an atom that is centered on each corner of the cell. So on a cube, there are 4 corners on the top of the cube, 4 corners on the bottom of the cube. So there's a total of 8 corners. If an atom is on the corner itself, that means that the corner is in the center of the atom. Then really half the atom is above the cell. And then if I look at the side, half the atom is outside the cell this way. And then if I look at the third dimension, which would be coming in and out, half the atom would be outside, either behind or in front of the cell. So if half of the atom is outside in each of the three dimensions, that only leaves half of a half of a half inside the cell. So each corner atom in a primitive cubic or in any of these structures, the corner atoms are only 1/8 inside the cell. 7/8 of the atom is actually outside the cell, which the unit cells are actually kind of stacked on top of each other and all around. So 1/8 is in this cell. The other 7/8 would be in other unit cells that we're not looking at. Okay, so that's the corners. If there are 8 corners, each corner is 1/8 inside the cell. I can do 8 times 1/8, and that tells me that from the corners, that's going to contribute 1 atom inside the cell. Then if I do the body-centered structure, again we have 1 atom on every corner, so that all the corners are going to contribute 1 atom into the cell. And then there's going to be another atom. If you look at this picture, there's 1 atom that's actually right in the middle of the cell in the center, completely inside. So there's 1 atom inside the cell from the body-centered atom, plus the 1 atom from the corners. So inside a body-centered unit cell, there's a total of 2 atoms inside. 1 from the corners and 1 from the one that's in the middle. Okay? Then we go to face-centered, the third one. Once again, the corners are all occupied, so the corners are going to contribute 1 atom inside the cell. And then now in the face-centered, each face or surface of the cube, there's going to be 1 atom that's right in the middle of that face. And if it's in the middle of the face, that means half of it will be outside the cell and half of it will be inside the cell. So each face contributes half of an atom into the cell. So then I think about how many faces are there. On a cube, there'd be 4 faces around it, plus the top, plus the bottom. A cube has 6 faces. So 6 times 1/2, all the faces are going to contribute 3 atoms into the cell. So my corners give 1 atom, my faces give 3 atoms, so that's a total of 4 atoms inside this cell. So if you want to memorize, simple cubic is always 1 atom inside the cell, body-centered is always 2 atoms inside the cell, and then face-centered is always 4 atoms inside the cell. That is the information we're going to need when we get into the problems at the end of this PowerPoint. So again, we go through these. When you talk about metals, there's a lot of information there, but specifically an alloy is a mixture of metals, so you should have some knowledge of that information. We get to ionic. This is where we get to our 3 types of cells that we mentioned. There are many more types that can exist, but instead of making you learn all of them, these are just 3 characteristic cells that are common, so they're the only ones you're expected to know. When you look at crystal structures, if you have a given compound, it's pretty difficult to decide what type of cell it's going to exist in. Again, there are ways you can figure that out, but we're not going to go into that in this class, so don't worry about that. You don't have to predict the type of cell at all. You do want to know how the radii fit in, but again, we're going to get to a problem in a little bit. We'll talk about the radius of the atom and how it fits in with the edge lengths. Do want to know what the coordination numbers are, so again, you can read about that. And then covalent network, the different types of solids listed here. The one that's not really mentioned in any other slides are amorphous solids. Again, the book talks about it, but those would be solids that have no clear structure. The atoms are fairly randomly arranged. Again, glass would be a good example of an amorphous solid. A few of the general properties are listed here, but again, I want you to kind of learn those on your own. And then basically, if you follow the instructions I've given in this video, and then if you are capable of answering all the Mastering Chemistry questions for Chapter 12, then really that's what I expect you to know for this chapter relating to the test. All right, so now we have one example here. of a problem that can relate to specifically the unit cells, and ionic solids is where these apply the most. Actually, ionic solids and metallic solids. Okay, so we have nickel. Nickel is, of course, it's a metal, but the atoms are arranged in a very regular structure. And if you simplify it down, it actually matches up with a face-centered cubic cell. So they're providing to us the density of the metal, and then they want to know, given the density of the metal, knowing that it's nickel, and knowing that it's a face-centered cubic arrangement, can we calculate the edge length of the unit cell? So how long is one side of the unit cell? Okay, now the answer is given here, but let's take some time to work through the math. So essentially, on my board I've already drawn a cube. We have a face-centered cube, so I know that I have an atom on the corner, and it's actually on all the corners, so I'm just going to draw on the front face. And then I know that in the middle of the face there's another atom, and actually these should all be the same size, but when we draw a face-centered cube, the atoms that go across the diagonal, so the ones in the opposite corners and then the one in the middle, they should be touching each other. Okay, so it's not the best drawing. But that center atom should be touching this atom and this atom. Okay? Now, they gave me the density of the nickel. It was 8.908 grams per centimeter cubed. I know that if I know the density and the mass, I can find the volume. Okay? Now the volume of a cube is length times width times height, and since this is a square cube, I know that the length, width, and height are all the same. So basically, if I can find the volume of the cell, then I'll be able to take the cube root to find the edge length. Okay? Now how are we going to do that? Well, the density, again, it was given, is 8.908 grams per centimeter cubed equals the mass. So for this atom, nickel has a molecular weight, or atomic weight, of 58.69. Okay, so I know that each nickel atom weighs 58.69 AMUs. I also know that if it's a face-centered cubic cell, talked about a few minutes ago, it's going to have 4 atoms inside the cell, 1 from the corners and 3 from the faces. So I know that I have 4 nickel atoms inside the unit cell. Each one weighs 58.69 AMUs. So if I do 4 times 58.69, that's going to give me the weight of the atoms in the cell, which is going to correspond to the mass. Now my problem though is my mass is supposed to be in grams, and I'm going to have the mass in AMUs. So once I get that number, which will be 4 times 58.69, to convert it, you guys in 1211 learned Avogadro's number is the number of atoms in a mole. Specifically though, really, Avogadro's number in its true nature is actually the conversion unit between AMUs and grams. Okay, there are 6.022 times 10 to the 23rd atomic mass units in 1 gram of a sample. Okay, so I'm going to get that first weight, 4 times 58.69. Then to convert AMUs to grams, it's going to be Avogadro's number, 6.022 times 10 to the 23rd AMUs to 1 gram. That's going to give me the grams of the sample. So let me do that real quick. 58.69 times 4. So my mass in the cell is going to be 234.76 AMUs. And then I divide by Avogadro's number, divide by 6.022 10 to the 23rd. That gives me 3.898 times 10 to the negative 22nd grams. Now, it's a very small number, but remember, we were talking about atoms in terms of grams. An atom has a tiny mass. So that's a very tiny number. That's going to be the mass of 4 nickel atoms, which is what's in 1 unit cell. So I'm going to take that number and plug that in as my mass. 3.898 times 10 to the negative 22. I'm going to plug in for my density, my 8.908 that I had here, and I should be able to solve for my volume. So the volume is going to be the mass divided by the density. So the mass divided by 8.908 gives me 4.376 times 10 to the negative 23rd centimeters cubed. Okay, now that number, again, the volume of a cube, if I take the cube root, that's going to give me the length of one edge. So, let's see. So if I raise that, or excuse me, took that cube root, it gives me the edge length is 3.52 times 10 to the minus 8 centimeters. Okay, and then the question asks for it in picometers. Well, I'm just going to skip over that. I think you could do that yourself. But if I change centimeters to picometers, then that's going to give me the answer that's on the slide, which is 352 picometers. Now, one more step that the question didn't ask me to do is it could have asked me to find the radius of the nickel atom. Okay, now how to do that? I know now that the edge length, from the center of that atom to the center of that atom, I know that that length is going to be 352 picometers right here. Okay? Now, if it asks for the radius, I have to do a little bit of math here because my drawing, while it's not perfect, it is accurate that the atoms in these corners are not touching each other. There's an empty gap in between, and I don't know how much space that is. So I can't use the edge length to find the radius of the atoms directly because there's a gap in between. But where I know there's not a gap is going across the diagonal. If I go from one corner of this cell straight across the face to the other corner, that is going to go through one radius of the atom, then the diameter of the middle atom, and then the radius again of the next one. So if I use the Pythagorean theorem, a squared plus b squared equals c squared, I need to solve for the hypotenuse there. So a squared would be the edge length squared plus another edge length squared, which is the same value. That'll give me c squared, and then take the square root. That value would be 4 radii, because it's 1 radius here, the diameter is 2 radii, plus the 1 right here. So that's a total of 4 radii of the atoms that have to pass through. So I could, if asked, take the edge length, use that value to find the diagonal, and then divide that value by 4 to get the radius of the nickel atom. Okay? I'm sure that there's probably a Mastering Chemistry question where you have to go through that process. Now, it works that way for face-centered. If you do simple cubic or body-centered, that's going to change the arrangement a little bit. And for each one, you have to kind of play with the numbers to figure out what you need to do. All right? So that's chapter 12, all in one video. See you next time.